Yeah, hi everyone. This is our capstone presentation on intelligent text condition music generation. Uh, I'm Nikhil. This is Java, Zini and Jingshi, and we have worked over the last year on this project. Now going to the introduction, we all might have been aware of the ImageNet dataset that has been extensively used for computer vision tasks, specifically for image captioning and multimodal question answering. We wanted to extend this to a new modality, which is music. And we have built upon the works of DALI, which was text to image generation, and music VAE and Muse Morphos for encoding our music encoders. And the core of our models is using the training paradigm that was introduced in the clip paper that uses a contrast loss to align various modalities. So broadly, our work is to generate music from text. One of the biggest issues here is that most of the generative music AI machine learning models only use music as the modality. So both the input and the output are some forms of representations of music. As far as we were aware, when we started working on this project, this was one of the first attempts to try to align text and music, which are two completely different modalities. But our goal was also to be able to encode artistic features in text and be able to represent that in music and help artists in their creative music explorations. So our research question is it possible to generate text condition music? And our proposed solution that involves a training paradigm is we collect a lot of data, which we'll talk about later, that is just pieces of music linked with text. And after appropriate data processing, we go through the machine learning pipeline. And our machine learning pipeline looks like this, where we have a music encoder that generates music, and we train a multimodal clip model. This multimodal clip model lends to assess whether or not a given piece of music aligns with text. Once this submodel is trained, we do an inference pipeline where, given a piece of text, the decoder is continuously retrained until this discriminator says that the given piece of music aligns with the text. So we have a kind of GAN architecture here. We have a generator that generates music and a clip model that's a discriminator. Our scientific hypotheses are it is possible to learn a mutual latent space for representing music and text in the same domain using contrastive learning and cross-attention. It is possible to perform conditional generation from the learned latent space by training a music decoder during the inference. It is possible to evaluate the performance of generative model using existing metrics and datasets at hand. Yeah.
The major features of our project should include first, using representation learning to train an encoder to learn the latent embedding of an input music piece. And second, using text conditioned music generation to generate music conditioned on text prompt. There are two groups of intended users. The first one is machine learning researchers who should be able to access our source code and use our model as the starting point to generate music and explore other downstream tasks, and also further improve their model, and they will be provided with a script or interface to run the model. Another group of intended users are multimedia artists who will be able to access using the end-to-end model to generate music. This figure shows our system functionality with relation to the two groups of intended users, machine learning researchers and multimedia artists. The non-functional requirements for components, we have the clip-based encoder that converts text to latent representation space, a decoder of music VAE style that generates music, and a discriminator that evaluates the quality of the music. The constraints and expectations are, first, the latency during inference should be within acceptable range, and second, non-deterministic results. Resource requirements for data consist of sufficiently large music to text dataset and an instrumental music in symbolic format with text annotations. Computing requirements includes computational heavy, large RAM, and GPUs required. And the potential human resource requirements that we need are human in the loop during model training and human evaluation during on the generated music. For design considerations, our assumptions are data processed by the system only contains music without vocals. And since art appreciation itself is subjective, so there's no universal optimal solution to the problem. The computing resource constraints will be mainly using AWS and Google Colab, and we'll mainly using datasets only available online, and we have a limitation of the evaluation type. The design methodology consists of 3 components: the data pre-processing module, the model training module, and the evaluation module, which we'll discuss later in detail. Tools and dependencies we use include Python 3 Magenta, RTMedia, and Python RTMedia. The challenges we face during the data design process is that there are only few existing multimodal music datasets. So we need to create our own datasets by merging 4 existing datasets. We use the LAC MIDI dataset as starter raw MIDI files. This dataset consists of symbolic formatted music data that could be matched with the files from the Million Song dataset. We use the LAC piano roll dataset as target files to filter the raw MIDI, and the piano roll consists of a list of music files of various genres without the lyrical content. This filter dataset is fed into the feature engineering process. And the output of the feature engineering is a set of REMI files. We chop each of the REMI files into smaller files with only 16 bars. This will better fit the required input format of our model and also provide more training data. We use the list of matching data provided in the multimodal music dataset to obtain a list of REMI files with unique identifiers that are able to match with our text Amazon review data. The process Amazon reviews are then matched with the REMI files as data and label tuples for the training process. And challenges we face for the feature engineering designs are a series of pre-processing procedures are required to clean and prune the music data and convert the data into our desired format. So it is non-trivial to implement the end-to-end data pipeline. Our feature engineering design mostly works with the different file formats. As mentioned earlier, the MIDI is a format for digitally stored music using a set of events to denote how music should be played. And REMI is revamped MIDI-derived events, which is a representation of MIDI data, following the ways humans read and understand them.
Now getting into more of the details in the model training design. So the first part of the submodule was the multimodal clip, which lends to align the text and music. And the way it works is we have a text and a text encoder, which is BOT, represents the text into embeddings T1 to Tn, and we use the Muse Morphos music encoder to represent music into various music representations. And then the contrastive loss is designed in such a way that the cosine similarity score is maximized for the pieces of music that align with the text, and at the same time the cosine similarity scores are minimized for pieces of music that do not align with the text. This way, the model gets an understanding of whether or not a piece of music is aligned with the text, and we use this as the code discriminator module. On the right side of this image is the generator. Given a piece of text, we again represent the text into text embeddings, and then we have a music decoder that was trained using the architecture of music variational autoencoder. So we generate pieces of music from latent space. Various pieces of music are generated, and when the cosine similarity score as calculated by this module is high, that music is picked. And at the core of both the modules is cross-attention. The cross-attention layers learn how to fuse and align the representations across modalities. So the query vectors of music align well compute cross-attention using the key and value vectors of language, and the query vectors of language compute cross-attention using key and value vectors of music. This way, the tokens of language lend to attend to the relevant tokens of music and vice versa. And the entire training process in detail, once the multimodal clip model is trained as described in this process, for a given piece of text, let us say we want to generate music for a scenario, and once the scenario is represented in the text, the music VAE decoder is continuously trained for around 100 to 200 epochs, until the multimodal clip says that the contrast to loss between the music and the text is good enough to go through. So what this means is that in the inference pipeline, traditionally, when you train a machine learning model during inference, you only have one forward pass. But in our case, in the inference pipeline, we have around 100 forward and backward passes, because the decoder is trained in every data point during the inference to align with the text prompt. So this is a conditional music generation that is guided by the clip. And regarding the model testing, we have majorly focused on computational metrics, where we try to assess whether or not the music aligns with the text using the same contrast to loss that we used for training. But the other ways in which we could evaluate is, for example, using downstream tasks. For example, if the text prompt is that a song that is sad, you could predict a text label that represents the sentiment of the text, and also use the music generator to generate the music and try extracting the sentiment of the music and see if both the sentiments align with each other. This way, the evaluation models are modality independent. The model which extracts a sentiment from the music need not have any understanding of the text, and the model that extracts the sentiment from the text need not have any understanding of the music. And the final evaluation type is to have human in the loop evaluation, because this is such an artistic task. It's very difficult to encode all of them into metrics, and this is one of the fundamental issues with the generative AI field as a whole. In this project, we focus more on the computational metrics for the time being. Now, coming to the risks and challenges, one of the biggest issues is that the quality of art need not always be good. Even though all the loss metrics and the error metrics are good, there is a lot of non-determinism, and just by tuning the parameters a little bit, there is a possibility that the final piece of music that you hear is very terrible, and in the next epoch it's again good. So when somebody makes use of such systems for aiding in the creative expressions, they need to be aware of such situations and be patient and use it as a tool rather than an end thing that generates a fine quality art. And second thing is high inference times, because we use the contrast to loss based discriminator to guide the synthesis of the generator. During the inference pipeline, we have to train decoder for every music, every text input, and this takes around 15 minutes time for 100 epochs. So you need to wait for 15 minutes for a given piece of text, which is still fine because musicians take days to compose music anyways.
So these are following slides are the plans we had from the previous semesters. First one is about data preprocessing, which includes collecting and preprocessing music data suitable for our projects. And we also have plans for multimodal alignment model. We previously had two tasks, which one is text to music generation. The other is text to video alignment. However, due to limitations and constraints, we have abandoned the text to video task this semester, and we're only focusing on text to music generation. And for the music generation model plan, our task is to develop a music decoder capable of generating music from latent embedding. And we also have model evaluation plans, which are developing a model evaluation module that performs the 3 model evaluation approaches described in our design section. For the above plans, we have all completed them. And this is a milestone plan we had for the spring semester, which we have already finished all of them in the previous semester. And this is our plan for this fall semester. And we have been constantly updating this. And till now, we have finished all of them. This is the result for our data preprocessing. Our data features include 4 components. First one is bar position, second one is REMI events, and third and fourth are 2 music attribute scores, polyphony class and rhythmic intensity class. And on the slide, this is an example of the processed REMI data with corresponding Amazon review labels that we matched with piano roll data. And we matched all unique million songs dataset tracks with the Amazon review dataset to obtain our track level training dataset. And we also used an external dataset Mumu to match the processed REMI files with Amazon reviews using an Amazon identifier field defined by Mumu. So on this slide, there are tables that summarize the statistics of the datasets we used. The large variance of the data and the label length and the sample data suggests that there is a high level of heterogeneity in our data. Therefore, we segmented each pieces into smaller chunks before feeding them into the model. This is table on the left is the event definition we defined to represent the data set after our feature engineering. There are in total 405 tokens. And on the right is an example of REMI data items. The REMI data items are in the format of a dictionary having name and values as their keys. So for the musical attributes we mentioned previously, rhythmic intensity and polyphony, they are calculated from the raw rhythmic intensity scores and the raw polyphony scores. Rhythmic intensity score measures the percentage of subbeats with at least 1 note on set, and the polyphony score is a bit more implicit, and it is defined as the average number of notes being hit or held and the subbeat. After computing the raw score, we then divide them into 8 bins with roughly equal numbers of samples, and then we assign a class to each music piece. This is our training results for our encoder. We have a table describing the settings and results on this slide. And for each setting, we have a plot showing the training loss per epoch. On the left, it is the training plot using full data, which is about 137,000 batches per epoch. And on the right, it is the training plot using only 10% of the data. We use a batch size of 8 and a fixed learning rate for the 10% of data training. Our model converged on the full data after 4 epochs and reached a lower contrastive loss compared to the model trained on the 10% of data, which converges after 6 epochs. Here's the loss curve of the decoder during inference. So you can see that the decoder converges before 100 epochs. And this figure is at around 50, 60 number of epochs. And the entire generation process takes between 10 to 15 minutes to finish. So the figure on the left here shows an example outputs from the decoder right after it goes through the inference steps. So we noticed a few issues with this raw outputs. For instance, the outputs contain an extremely dense distribution of chord events as compared to individual note events. One other issue is that the outputs normally contain more than 1 tempo events for each piece, which leads to inconsistent tempo throughout the entire generated outputs. So to resolve these issues, we introduced a few post-processing steps to convert REMI event representations to MIDI format. These include sampling the first chord for each beat and fixing the first tempo token as the tempo of the entire piece. So here are 3 samples that were generated using different textual prompts. Since the outputs contain 2 types of tokens, chord tokens and individual note tokens, we assigned 2 different sounds to help distinguish between these 2. We assigned an organ sound for the chords and a piano sound to the individual notes. So here, here's the first sample that was generated using the prompt "A Pop Song About Love."
And then the next one is the sample generated using the prompt, a melodious tune for coping with pain. And then this last one was generated using the input, a song about using artificial intelligence to generate music for a class of graduate students, which is pretty relevant. Well, so there's definitely a lot of room for improvement with these outputs, which we will briefly discuss on the next slide. But we do feel like these outputs could be useful for human artists to facilitate their creative process by providing them with interesting themes or chord progressions to sample from. Which is in accordance with our initial motivation for working on this project, which is to develop music generation models to help human artists to create new sounds instead of like trying to use AI to completely replace the human creative process. So now we turn to some limitations with our work that invite future work. So the first thing we note is that from the previous samples, the relationship between the textual prompt and the generated music is oftentimes not strong enough. We hypothesized that this could be improved by training a better text-music alignment model with a larger and higher quality data set. Another thing is the disproportionate number of chord events as compared to the note events in our outputs. And we hypothesized that we could deal with this issue by using a more sophisticated loss that regularizes on the number of event tokens that are being generated. And then lastly, we note that the music that's produced lacks consistency with respect to core musical attributes like tempo, key, velocity, etc. And for this, we hypothesized that we could mitigate this issue by either using a better design loss function or by imposing certain rule-based heuristics during the generation process to further confine the search space. And then looking back at our journey, this past 2 semesters working on this project has been an incredible journey for our entire team. It's been like a very challenging problem to tackle due to a variety of reasons. So we are like super proud of ourselves that we're able to like eventually push through all these challenges and arrive at where we are right now. We definitely feel that we've grown a lot together as a team during the course of working on this project, both in terms of technical skills, such as like working on complex code bases and like debugging model training issues, but also more importantly in terms of soft skills like how to work most efficiently as a team and how to react to unexpected situations by adjusting our plans accordingly. And we feel that these like the skills that we've developed and enhanced will for sure benefit us in our future careers as well. And then here's the list of references and some terminologies that are relevant to our work. And let's see some changes to the previous deliverables. And that is the end of our presentation. Thank you for listening.
All right, thanks very much, guys. Great job. So I think this was definitely the most open-ended of the projects that we had this year. And you guys spent a lot of time dealing with contingencies and doing a lot of learning as you went through that. what would you do? And this is a very specific question now. You learned a lot about this space, right? So if you were going to start over again, and I know you decided that video was out of scope, but let's just set that aside for now. What would you change in terms of either the relative emphasis, that put into certain parts of it? Because I know you learned a lot, right? So presumably, if you started over again, there are some changes.
Yeah. One of the changes is that there is not much to train in the text. There is not much scope for improvement in the text encoders because we already have very good large pre-trained models for text. So it's important for us to be able to very rapidly experiment with various kinds of encoders and decoders for music, which means that like at the way our code base is written, it's more modular to replace anything in text than to replace things in music, because we started with generating just music without any text, and then we added the text modules on top of the code base. If we were to redo it, we would first put the base as text and then keep adding the music encoder element, so that it just makes the process of experimentation much more easier. And then the second thing is that, as we discussed, we need to make sure that, so right now the music generation is completely model free. The music VAE is just a bunch of layers that has no information of any music rules, but we need to have these heuristics encoded into the training. But the tricky part of doing such things is you cannot backpropagate very easily through all such rules. So we need to create like a continuous form of rule, which we did not tackle this time, but probably it's important to think about that right from the beginning, since we now have a better understanding of how the output is going to look like. And then the third thing is the data set that we have trained is, first of all, very big for our scope of the project, in the sense that it takes a couple of days for the couple of epochs to go through, but still this is not sufficient. The problem is very challenging, and we are using dual layer transformers for each of the encoders and decoders. So we have millions of parameters. We first of all need even larger data set, but what it also means is that the training process of one iteration is going to take around 20 to 30 days for the music to align with the text with, for example, one GPU. So a better way would be to parallelize the training across maybe 10 GPUs, so that even then it can still be done in like 4 to 5 days. So we need to also have another layer of deep speed or deep scale between the CUDA layers and the model training layers for this parallelization to happen across multiple GPUs.
And I could probably add another point regarding like project management wise, that's like also related to Nikhil's remarks just now. When we're like doing the first like project plan, we significantly underestimated the amount of effort and time that's going to take for like integrating the music encoder part and the text encoder part, and then also the like the entire generation pipeline. It actually took us like an enormous amount of time to get like the whole system to work. So one of the outcome is that we didn't have enough time to like figure out how to do distributed GPU training, for instance. So yeah, I feel like this is a like good lesson to learn, like in terms of the project management.
Hey, Roger, did you have any specific questions you wanted to ask?
Eric, was that an invitation to ask a question?
Yes, it was, if you'd like to.
Yeah, I'd like to. Yeah, one one comment that comes to mind is there's a famous quote that talking about music is like dancing about architecture. And I guess one thing I wonder if you have thoughts about is that a lot of text about music has to do with emotion and texture and timbre and style. And yet, if you go to a piano roll representation, you lose. I mean, even a lot of emotional content is in the performance detail. So if things are quantized, you strip out even a lot of emotion. And so I just wondered if you thought about, what kinds of text could you hope to render through piano rolls, or I just wonder where the text mining associating audio, mapping audio to piano rolls, how much you feel is kind of lost in the translation there.
Guys, make sure you unmute before you answer.
Yeah, I'll attempt to answer this question. One of the biggest issues is that we need a data set that's multimodal in nature, where we have both text and music. We had internally in the team tried to figure out what are all the ways that we could create such a data set. No matter which approach we were trying to choose, there is always some loss of information. For example, the other kind of data set that we could have chosen is to separate vocals from music and use the vocals as the textual lyrics to align the music with the text. But again, it has its own pros and cons, and it's also not very straightforward to very clearly separate vocals from music. And most musics are like, typically, when you go to classical music, the pieces are so long, but the textual description is just one sentence. So that's not much useful. If you look at the text to image generation, for every image, you have lots of alternative texts. This is not a case here. Typically, so I think a better idea would be going forward to increase to enhance the model by combining all these ideas of creating the data set, not just the Amazon reviews, but also the lyrics, but also the comments, but also descriptions in Spotify, like everything, combining all of that, and then trying to see if our encoders can learn these alignments.
Yeah, and then just to add on to Nikhil's point, there's a visualization that I want to show because it's funny. So like here's like a word cloud analysis we did on our text training data, and so the thing we noticed is that like a lot of the is that the text data that we have mainly are like descriptions about the musical genre, and there's like not much information about, say, the performative style or like the timbre of specific sounds, etc. So yes, that's what we are trying to capture with the piano roll representation. And I think it's a great point that the piano representation is like pretty limited in terms of its ability to capture more fine-grained details about the music. And I feel like it's definitely a very promising direction for future work. It's gonna be like a lot more challenging to be able to generate music that has timbre or that level of details, because that's gonna make the search space to be even larger by adding in more knobs that you could use to describe the music. So yeah, I feel like it's a very challenging problem, but definitely something we'd be willing to explore more about if
yeah, so I want to remind you, Joey, that when we started on this, one of the things we talked about is taking the same piece of music and then being able to recognize when it's played in the style of a certain musician. So I think one of the implications of what Roger is saying is that you could completely pivot where you're not trying to analyze many different songs in order to generate novel songs, but you might want to analyze many different performances of the same piece in order to generate like certain kinds of renderings. I think also the idea that you can change the rhythm of any particular piece to a samba or a reggae beat or something like that is a really interesting way of separating things out. But you're right, you would need to basically create a data set that holds certain dimensions constant and then varies others in more interesting ways. And when you're just sort of working with the piano roll data that you find. Roger, did you have any other questions? We have about 1 more minute here.
Yeah, I was just thinking as you were talking, I wonder if there are, I mean, images have worked so well, but I wonder if there are any data sets of abstract images. Images are sort of referential in that they're representative. And so they actually have identifiable objects in them, but music doesn't.
Mhm.
So I think that's part of the problem. Yeah, I guess I don't have any other questions.
All right, well, thanks for coming, Roger. It's great to see you. Take care.
Yeah, thanks. Thanks for the presentation.